Hello.
பழைய பாட்டு தானே அது சொன்ன மாத்துங்கன்னு மாற்ற மாட்டேங்கிறீங்க.
பேக்ரவுண்ட் விண்டோஸ் அப்டேட் ஃபுல்லாக லோட் ஆனால் தான் இல்லை இப்போ சாங் போட்டில் ஒரு ப்ராப்ளம் லாஸ்ட் டைம்.
So shall I start? Okay. Welcome everyone. தமிழ்நாடு அறிவியல் இயக்கத்தோட சயின்ஸ் லெக்சர் சீரீஸ் நம்பர் 15வது சயின்ஸ் லெக்சர் சீரீஸ் we are going to start. Last 3 lectures, this is the third one, is on Nobel Prize 2019. The first one was held in Institute of Mathematical Sciences, which is my own institute, on medicine. And the second one was held here on the physics aspects. The third one is on the chemistry. Okay, as you all know, our life depends on cell phones, various things, etc., which is powered by one of the most important, practically useful, most important instrument, which is the cell, lithium-ion cell. And it has played such a major role, Nobel Committee has decided to honor that particularly useful activity of chemistry this year, and they have been given the Nobel Prize. To speak about this, we have 2 eminent professors from Indian Institute of Technology, Chemical Engineering Department, Dr. Raghuram Shetty, who is the first speaker, followed by Arvind. He will be the second speaker. In fact, I talked to them through my friends in IIT, and they are even willing to answer your questions if it is required in Tamil, if you ask any question. But if there is any difficulty, we'll manage. I don't think that difficulty will be there, but for the purposes I'm just mentioning. Now we're going to start the program, and my friend Ramanujam has come. He was supposed to stand here and speak. Okay. Anyhow, we have the program started now. First, Vijayan will speak something about Tamil Nadu Science Forum for a few minutes. Before that, we will have the conventional activity of this library, which has been functioning on Tamil Thai Vazhthu, which is for 2 minutes. Following that, for 2 minutes, few minutes, our friend Vijayan, who is the main coordinator for all these programs, will speak about Tamil Nadu Science Forum, so that you can participate in future programs. We have been organizing 15 lectures every month, definitely one, and we will continue to do that for the next month, January, February, March, April. Usually when summer vacation and others are happening, it is going to be at low level, because students and college people, mainly our backbone of attendance is from here. So my request all this to people to come forward. You will find it better because the voice level will be better for, you can even take any of these seats also. And you will be able to see the programs better. Sorry. Okay, now we'll start with Tamil Thai Vazhthu. Thank you. Vijay.
So I'm not going to take much time. Tamil Nadu Science Forum has been introduced to you many times, but I find a lot of newcomers this time. That's the reason we want to introduce Tamil Nadu Science Forum again. TNSF is a voluntary organization involving in popularizing the science. So it was founded in 1980s. So founder member is Dr. TRG. A lot of other stalwarts are sitting here. From 1980 onwards, it was functioning well, and it was confined to Chennai city alone. Later, in middle of 1980, it was extended to the entire Tamil Nadu. So we conduct the science march. We conduct the literacy movement. We are also organizing, publishing a couple of magazines. One in Tamil, it is called Tulir. Other one is in English, Jantar Mantar. Both of them are available in the desk. You can subscribe it. Tulir was running for the last 30 years. It was started in 1989. It was a best children's science magazine without any advertisement. It's standing on its own leg. Same way, Jantar Mantar. It was started in 1991. It was 92. We recently celebrated the 25th years of the Jantar Mantar. So we have. So finally, we want to focus more on the higher science. So one of the wings of the Tamil Nadu Science Forum is working on the popularizing the higher science. So that's the reason we started with the popular science lecture series. So it was started in the last year to commemorate the memorial lecture of Stephen Hawking. So it was the first lecture was on cosmology. Since then we have 15 lectures, 15 events has conducted. This is the 15th event. So last year also we have done about the Nobel Prize for 2018. All three topics are covered. This year we are covering the three topics. This is the third topic. So every month we are having the lectures. So I call upon you to become the Tamil Nadu Science Forum, member of Tamil Nadu Science Forum. Membership fees is 30 rupees is annual subscription. The subscription and you can get the form and pay your subscription outside. We have a desk for enrolling the membership. You can also, we also display the science publication. Science Forum is running the publication as well. We are displaying our books, science book, popular science book published that has been displayed outside. When you are going out, you can purchase the books as well. With that, I can. That's my appeal. Okay.
There's one small thing which I wanted to mention since he raised various things. You know, this year, December 26th, there is a very important event in Tamil Nadu and Kerala, which is called the annular solar eclipse. In Tamil, Valaya Surya Grahanam. So we are lucky that it will pass through Tamil Nadu. We are unlucky it will not pass through Madras, but it will be about 85%. Now, if you are lucky and if you have relatives or somebody or any other activity, you can go to Coimbatore, Tirupur, or Karaikudi, or Madurai, any of these places where, or even Wayanad, if you are in Kerala, you can, the total solar eclipse, annual solar annular solar eclipse will pass through. There is an attempt by Tamil Nadu Science Forum to campaign in schools. In fact, I myself went to one of the school, so that people will take part as a major activity. In the superstitions associated with this solar eclipse, we would like to smash it. We want to say it's the greatest event where the dance of sun, moon and earth in the space is happening very, very, very rarely. And it is when it is rarely, it happens in other places. It happened in Agra, it happened in Patna, it will happen in Brazil, it will happen in South America, etc., other places. And it is happening here in Tamil Nadu. Do not miss this chance. It's a great celestial drama lasting, the totality will last only 2 minutes. That celestial event of 2 minutes is worth seeing. I have traveled 1,000 kilometers to see the 2-minute drama. So I would urge all the people to take part in this program, which is Tamil Nadu Science Forum is organizing in Madras Beach. The attempt is to get thousands of people assemble there maybe around 8:30 in the morning, and it will be over by about 10 o'clock. So the eclipse will start around 8:40 or so, and 9:30 around that time, the totality or maximum in Madras will be there, and there is no fear, nothing will happen. Only thing is you have to be very careful in viewing the sun, because it is so bright. If you view the sun for a long time, like half a minute, 1 minute or something, your eyes will be spoiled. So there are various ways in which it can be seen, and Tamil Nadu Science Forum is also going to produce several specs, filters, which can be used to see that. In addition, very simple equipments will be there if you come there, and it is worth seeing. So, in fact, in Calcutta, when the previous total solar eclipse, not annular, total solar eclipse took place, about 2 lakh people gathered in Diamond Harbour. So this is the kind of activity which we should be celebrating as the greatest drama created by nature, where 3 major players, sun, moon and earth, are playing out there. So December 26, mark your calendar, morning 9 o'clock. 9:30 is the exact time. 9 o'clock, you should probably try to make it. I myself will be going to Tirupur. Thank you. Now I invite Dr. Professor Raghuram Shetty. He is from Department of Chemical Engineering, and he is an expert on the actual, both of them are experts on fuel cells. Okay? So they will explain one after another, and any questions we will take up after the lectures. Thank you.
Good afternoon, everyone. Hope I'm audible. Yeah. Thanks to Tamil Nadu Science Forum for inviting us, and then. Okay. So thanks to the Tamil Nadu Science Forum for inviting us today and asking us to present this lecture on lithium-ion batteries. I think it's a pleasure to be here. Good to see wide audience. I think I see college students here. Today I kept the lecture very general so that all the audience can understand. I didn't put too much scientific content into that because sometimes you get lost if there is too much technical. But I kept it so open that you should be able to understand why the 3 people received the Nobel Prize and what was the contribution made by them to the lithium-ion battery technology. So just to start with, I think these are the 3 people. I think John B. Goodenough, Stanley Whittingham, and Akira Hoshino. So these are the 3 scientists who will be receiving the Nobel Prize I think next Tuesday, I think 10th of December at Stockholm. So they will be receiving the prize for the work which they have done on lithium-ion batteries. And so Professor Goodenough is the oldest person to receive a Nobel Prize. His age is 97. I think it's close to century. I think his work was recognized much later, but still I think he is one of them. He is a German born and he is working now at the University of Texas at Austin. He's a chemist. And then we have Professor Stanley Whittingham. So he's a scientist from UK. So he's now in the New York, in the State University in the New York. So he was shared the Nobel Prize along with Professor Goodenough and Akira Yoshino. He's a Japanese born scientist. So in the initial days, he worked in this Ashai Keisei Corporation. So it's a chemical company. So he's a chemist. So he worked on a chemical company. And later he moved to this particular university in Meiji University, again in Japan. So all these three people had made different contributions to this technology, and that's what we'll be looking at today. And all of them are there in, I think he is 97, I think they both are in their late 70s. I think one is 71, one is 79 and so on. So the work they did is not now, I think 30, 40 years back. That's where they did the work. But I think in research, I think we all may know, it will take a long time before any fruitful result is achieved or it is recognized. So it's a long time. So we do any work, I think most of you may be researchers or willing to do any work. So it will, don't expect that it's recorded immediately. It has its own time. I think when the time comes, I think it will ripe and then you will get the result for that. So that's what has happened to all these three people. All of us in one or the other form are using the lithium battery today. People have the cell phone in their pocket or in their bag, and each of them will have a lithium-ion battery. So that is one application where you can see the lithium-ion battery has made a revolution. And there are other applications like even the laptops, even the tablets. So these are all little low power application. On a little higher end, we have e-scooters, I think, which is getting very popular these days. And then we have e-bikes or other power tools and other things which are a little on a higher side. And then still higher, we have tools for certain medical devices. Sometimes you cannot connect everything to a power plug. So you need an independent power source. So we have some medical devices, and the UPS as a backup is one thing. In certain gardening tools, you don't want to plug into a socket, so you can use them. And further higher is the energy storage device in terms of renewable energy storage device, because the world is moving away from the fossil fuel technology. People are looking at solar and wind as an option. So they all have their own limitation because the sun is not there all the time, wind is also not there all the time. So you need the power in the evening or in the early morning where the sun is not there. So how do we store that? So sun is there during the daytime. So how do we store them and how do we reuse them? So that is where the energy storage technology will play a major role. And all those who have had solar installation would remember that, so nowadays people have, generally it is lead acid batteries are widely used for these applications. But the lifetime of the lead acid battery is very, very less. So a solar panel would work for about 20 years. But this lead acid battery would work for only 3 to 4 years at the maximum. In the lifetime of the solar panel, you have to change your battery at least 4 to 5 times. And that expense is much costlier than your total solar panel itself. So those are some of the bottlenecks why the renewable energy power is not reaching to the common people. Among these are the application in which the lithium-ion battery has touched its presence. And one other thing is the electrical vehicles. I think I didn't put the car here. I think that's, so then you can see, I think in Tamil Nadu, I think auto rickshaws were recently started. Even in, you may all remember, in the Delhi, every winter we have an issue because of the air quality. People in the Punjab and Haryana, the farmers, they burn the from the agricultural field, so they all get accumulated in Delhi and it pollutes the air there. And Delhi government has taken steps, and them, they tried is to bring in this odd even formula. So one day the odd number vehicles will go, one day the even number vehicles will go. So if you look at the context in which is done, so they all wanted to reduce the number of vehicles on the road. And all these vehicles are powered by fossil fuels, and they are the one which creates, I will add up, I think, additional pollution to the air. And all the rickshaws, I think now the rickshaws in Delhi has been replaced by lithium-ion batteries. So these are few steps which are taken so as to reduce, I think, the pollution or global warming in general. And so mobile phone, I think we don't need to say, I think it has revolutionized India because I think the old generation people remember. So to communicate from one place to another place, let's say 30 years back, you have either, they had that time they had that inland letters. You are a postcard. You need to write a letter if you have to send a communication to a person in a far off place. If the son has to write something to his mother in the village, maybe he is in a Kashmir and her mother is in Tamil Nadu. So it will take about 2 to 3 weeks for the letter to arrive. And if the mother is illiterate, I think there will be a postman or a teacher in that particular village who will translate that to her mother, and then she will reply back, and that the message get transferred back to him about another 2 to 3 weeks time. So the technology now can have an instant communication. I think that 3 to 6 weeks of time has been considerably reduced. So now this mobile technology has revolutionized, I think, our communication. We had a lack of, I think, the instant communication was not there, I think 30 years back. And today the situation has changed. And also in terms of development, the other countries are far ahead of us. So the 2G technology was 3G, the 4G and so on. And everything came to India after, let's say, 20 years or 15 to 20 years later. That's how all this technology came. But today I think the 5G technology is going to come in time where the rest of the world will also have the 5G technology. So India has had a huge leap in the mobile phone technology, and for all of these, I think the lithium-ion battery play a major role. In addition to the networking, I think the battery capacity have play a major role in this technology. And if you're looking at the application, so we have the consumer electronics. I think every gadget has some form of other lithium-ion batteries. And the one other thing is we have this automotive industry. I think it's not as much as in India, but I think the rest of the world has already started to move towards the battery technology. So India, and we are at just the beginning. And then we have energy storage application. That is where the renewable power gets stored. And then there is industrial regular UPS and other storage will come. So these are the major applications in which lithium-ion battery has penetrated in. And this, as of now, I think the global battery consumption is set to increase at least 5 times in the next 10 years. So this will place a huge demand on the availability and the price of lithium-ion battery. And people had put in a lot of investment. I think all the company whichever makes battery has invested in lithium-ion battery, even a forecast that their business would flourish in the future. And the electrical vehicles, I think in this year itself, there are several companies who have launched hybrid vehicles to start with. So the IC engines have ruled the world for the last 200 to 300 years. But now we can see the hybrid vehicles where you have both the battery and the IC engine coming together. So that is the beginning of this. So in the future will this will take a lead, and then it can go to another 300 years before the fuel cells comes in at a very later stage. And so this is the distribution in which the lithium-ion battery application is used. And just to give you a context, the UN, the United Nations, every a few years, I think they identify the problems which exist in the world, and they come up with, I think they wanted to eradicate this in the next 20 to 30 years. And if you look at that, I think we have like poverty, hunger, good health, and so on, quality education. So the health or the clean energy. I think this is the alternative, and clean energy plays a major role in this scenario. So UN also has recognized that clean energy is one way in which people can make the advancement in life by employing all of this. And if you look at the history, history has taken a long road before the technology what we have today. I think people lived as animals and then transformed. I think they developed, fire was invented and then it got transformed, and today we have tablets and the laptops in the hand to walk on. And this evolution, if you look at, so people tend to have a control of the energy, and earlier time it was the fire, then maybe now we wanted to store more and more energy in terms of technology where the battery can replace that fire. And the timeline, if you look at, I think the slide is not clear here, you can see. So the fire, the early man started to learn how to control fire. And so that was the energy of that time. Fire was the starting point. And then after several years, I think people started to use the horses and the donkeys for the animal power was used for to do work. And then as it went along, people started to use solar. I think the earlier invention, I think even 3000 BC, people started to make salt. I think from seawater, people have made salt. So those are again a storage of energy in the form of solar energy here. Then we had this boats, which was wind energy, so the wind can able to sail the boat across. Then coal was invented much later. I think the coal was again a condensed form of energy which came into picture. And then the steam turbines were invented about 1829. And then after that, the oil was invented. So the oil invention was a great revolution where we have the IC engine. The IC engine primarily runs with this oil. And then it's about 180 or 170 years ago, electricity was invented. So Thomas Alva Edison invented this light. And then the nuclear power came into picture, and then there is a solar energy. And then that was the beginning of a solar energy. And then over a period of time, people realized that the oil is present in only one place and concentrated in particularly in the Middle East. And then so there were war fight was there, and then that is where people started to look for technology other than fossil fuels. So that is where the solar, the wind. So it was about early 1900 was the 1990 was the beginning of the invention for alternative technology people look at. And battery as along these lines. So if you look at the research which went in the battery, so here if you look at, people always wanted to store, I think they wanted to store the energy in some form in which you can use it at a later stage. So along this direction, the battery also came into picture. So the invention started much earlier. It's about 1800. This is where the first battery was realized. So this is Volta. I think all the voltages what we use as volt. Lithium-ion batteries as 3.5 volt, or even the zinc-carbon battery has 1.5 volt. So that volt is coming from the. So is the first person who invented this battery. He's an Italian. So what he did was he took two materials. You had silver and a zinc, and placed a cardboard in between, and he had some aqueous solution of ammonium chloride dipped in it. So that was able to get about 1 volt of current on 1 voltage he was able to get. And then he made them in a stack. So he put them, so depending on how many he put, so the voltage also correspondingly increased. So that was the first invention. It was realized you can produce electricity and you can use them. So earlier times, I think he presented this to Napoleon. So any invention, I think you maybe go and present yourself to Chief Minister or Prime Minister of the State of the Head. Same thing he did here in about this a few years later. So he presented this to Napoleon at that time, and he was able to demonstrate that a material can produce current. And then he was able to stack it up. You can increase the voltage or the current depending on how do you stack up series, or you can put it in parallel, so that the voltage is also increased or the current is increased depending on the configuration you have. So this has these batteries, all these two metals put together in between a separator. Here the cardboard was used, and he dipped in two different in an electrolyte so that the electrolyte passage is also there. It has to be wet, and it has to the electrode should be there. So if you look at this configuration, so a battery should have anode and a cathode, and it should be separated by a separator. These three things are very essential for a, and then this conducting. So that is where this electrolyte, here is ammonium chloride, the electrolyte was used. So you should have an anode and a cathode and a separator, and the separator is just to separate the anode and cathode, and you need some media to conduct. So that is where your solution or conducting solution also comes into picture. So this is the first battery which was produced in that time. Until today the same configuration is there, only the materials have changed. So that's what I'm going to take you through. And so this is what's about 1800. A few years later, it's about 1836, Daniel cell was invented. So here, so if you look at the configuration, silver was used. Silver is a little expensive material. So people always look for a cheaper material so that it become cost effective in this process. So Daniel replaced silver with a copper. So he had a copper container, and then he had a zinc electrode. He had a copper and zinc he has used, and then he had put a pot, a porous pot inside this zinc. So this container has copper sulfate in it, and then he had a zinc electrode in which there is a sulfuric acid in it. So if you look at, so we have copper as an anode and this cathode, and then in between there is an electrolyte. So we have copper sulfate is also there, sulfuric acid is also there, and the separator is this porous plate thing, the porous pot, which is the separator. So he was able to make this particular configuration. The same setup again gave about 1.1 volt electrical power. And so he showed this is Michael Faraday. So he's a well-known electrochemist at that time. So he demonstrated that to Michael Faraday. And so compared to the earlier configuration, so he was able to get to a cheaper material, and then he was able to attain the same voltage what Volta was able to get. And several years later, it's about 1859, Gaston Plante. So he was the first person. So the first two batteries what you see, it's like our, we call this as a primary battery, like you use it once, and then once the power is over and you discard it. Okay. So and this is the person who invented what we call as what we use as a rechargeable battery. So you can use it multiple times. So it's not just once, you can use it more than once. So he has taken a lead electrode, and then he has two lead electrode with sulfuric acid. He converted this lead during the oxidation into lead oxide, and then during the reverse this will convert back into lead. So basically the lead oxide will go into lead sulfate, and even the lead will also go into lead sulfate. It's a reversible reaction. So we have reactions which is a one-side reaction, and also there is a reversible reaction. So he was able to employ this reversible reaction to produce this particular configuration. So these are the earlier batteries, and so you have a sulfuric acid bath, and you have two electrodes which are made of lead, and then you can charge them. You have sulfuric acid as an electrolyte. You charge them and you can use it for any application, and once it is discharged you charge them again. So these are the batteries like we have the horsepower or any, so you don't need any specialized person to make this. Even till today you take two lead electrodes, put it in a sulfuric acid solution, this battery would work. So these are very robust batteries, and till today I think all the cars or any vehicles which we use, the scooters or anything you use, I think they all have still today the lead acid batteries. Okay. However, the only disadvantage here is, the lead is a heavy metal. So these batteries are known since 1859. We can ask why they are still not being used in the commercial e-vehicles, we can ask. But they are very materials, so that is why they can make it to the thing what it has done now. So going along, so with this, the battery can be classified into two different types. we can say that one is a primary type and it's a secondary type. Also call it as a wet cell or a dry cell, depending on if you use completely a liquid media, it is a wet cell. You can have a partially liquid media, like you have a cardboard and you have soaked something, so it appears dry though there is a wetness inside. So there are two types, we can classify them. So the primary battery is the one, it's like a use and throw battery. Once we use them, you cannot reuse it. Whereas your secondary batteries are the one you can charge it and recharge it again and again. And two concepts, terminology which we use here, one is oxidation and a reduction. So usually a battery has an anode and a cathode. So in an anode there is an oxidation, while in the cathode there will be a reduction. During charging, during the discharge process, the opposite will happen. So same material can get oxidized and can also get reduced. So it is like oxidation is giving away, you give electron, or you take electron. So these are the two processes which generally happen in the anode and the cathode of the batteries. And so to give examples of these cells, these are the common batteries which we use in our today life. So all of them are primary batteries, so they all use only once. And if you look at, I don't know how many of you have opened the battery and see what it is there. I think if you have dissected the battery to see what material it is there. I think when we were children we used to do the same. To remove that, you can see, I think this is a battery which is very commonly used in these days for a wall clock or any torch light or anywhere you use. So you can dissect this and it's there. So if you open it, though it is called zinc carbon battery, the carbon is only an additional component which is added. So you have a zinc which is used as an anode, and then you have a carbon. This carbon is mixed with manganese dioxide, MnO2. So this is your cathode. So this is a cathode. Carbon is a carbon rod which is a support. Over that you mix MnO2, and then you have a zinc, and in between there is an electrolyte. So you have a separator. It can be a filter paper or a polymer, you can use it, and that is soaked with some electrolyte, ammonium chloride or so. So this battery will give about 1.5 volt, and so here the zinc is oxidized and the manganese is reduced. So there is an oxidation and reduction reaction which will happen. So that's why you get 1.5 volts. So it's a definite amount of energy which is stored in this container. So once it is used and once the reaction is over, and you have to discard them. And keeping that in mind, so you need materials for anode and you need materials for cathode. So if you look at, these are the two materials you would need. People in chemistry class would remember there is something called as a standard electrode potential. That means each metal can either give an electron or take an electron in comparison to hydrogen. Hydrogen is set as a 0. So compared to that, either it can take an electron or give an electron. So if you look in that series, so lithium comes into picture. So lithium can easily give away electrons. They have an ability to easily donate electrons, and the voltage is about 3 volt. I think if you have lithium as if lithium gives away an electron, you can get 3 volt. On the other side, if you look at, you have, so these are materials which are one side which is, yes, ability to easily give away electron. There are other materials which can accept this electron. So here we have fluorine and lead and so on. But fluorine is a gas, so it's very difficult to make a battery with a gas. So combining fluorine and lithium would be the best combination, because you need two materials which are in two extremes. One can easily give away electrons, another can easily take away electrons. But it's not possible to make these two, because lithium is though it can give away electron, the fluorine is a gas which it's very difficult for it to put it in a battery. So it's practical difficulties are there. So the other thing, if you look at that, where the lead is in the top of the series, that's why lead was invented long back. So if you go along this direction, so you need to choose material which has the ability to take this electron which is given by lithium. And one other constraint with lithium is, I think all the college students may remember, sodium you might have used in your class 11 or class 12. If you just put it a small amount of sodium outside in the water, it will catch fire. So sodium, you cannot leave it outside. It has to be stored in corrosive. in the lab they store it in the case. So lithium has a very similar property that of a sodium. So you cannot expose it to ambient air. So that is one constraint we have. So the lithium has to be kept in an inert atmosphere. All these lithium batteries, whatever the work is done, so they are never done in an open atmosphere. So you do it in a, we call as a dry box. So there is no oxygen is there, no moisture is there. So you do it in a box in which is free of moisture and free of oxygen. Usually it is nitrogen or argon is purged in that particular box. All the assembly work is done within there. So lithium is a material which can easily catch fire when it is exposed to ambient condition. So that constraint is there. Unlike your lead acid battery, you can just put some sulfuric acid and leave it open, then you will always get a voltage. Whereas lithium has a constraint. So that has to be taken into mind. And if you look into the periodic table, so this is how they have chosen this material. So this year is the 150th year of the formation of the periodic table. I think periodic table was done about 150 years ago. And now this Nobel Prize has come for this battery technology. And here, if you look at this series, so we have the first element which is hydrogen, helium, and then lithium. Hydrogen gas, helium is a gas. So as I said, it's very difficult to make a battery with a gas, so that has its own problem. So the nearest or the first metal is lithium, okay, and that is the lightest metal. So if you recall the periodic table, so higher is your number, heavier will be the metal. So lithium comes in the first, so the first metal is lithium. This is the lightest metal, and to have a battery, you need to choose two material I said. One you can choose from this end. Another thing, so these all of them are a very good reducing agent. They can easily give they have excess electron. They can easily give an electron. This side of the material have less electron. They accept electrons. So I think, so these are reducing element. These are oxidizing elements. You can choose in that way. So you can choose material of different combinations. So lithium is here, fluorine is here, but fluorine cannot be used. So this is a gas. So this is a gas. So the possible next could be a carbon or a silicon. So if you make these two combination, you can able to get a better battery material. So these are the things which went into the thought process of the scientists before they choose material for the lithium-ion batteries. And looking at secondary batteries, so that is earlier I showed an example of a primary battery. Secondary battery technology has been there. So we have nickel cadmium, nickel metal hydride. I think later metal hair battery. I think Professor Arvind Chandran will talk about the metal hair batteries after my lecture. So these are secondary batteries. Those are rechargeable batteries. You can use them. You can reuse them by charging again. And they have been there. I think the nickel and metal hydride batteries are there for a while. Again, so you use nickel. Nickel, if you look into this series, so it's much heavier. So compared to lithium, nickel is much heavier. So those batteries have been there, but they didn't make the revolution what lithium ion did because of the weight which it has produced. Yeah. And there are different casings which are used in which these battery materials are put in. So I'm sure most of you are popular with this. So we have the regular battery, which is the AA battery, which is used in several applications. Then some application also use this AAA battery, so they are a little smaller in size. And then we have C battery, A battery, and so on. So this will produce about 1.2 volt nickel metal hydride battery. So these are, most of them are rechargeable batteries, and about 1.2 volt nickel metal hydride batteries, and so on. So these are lead acid battery earlier times. So now people are moving towards lithium ion battery. And all of these are secondary batteries. So these are primary battery. This is again lithium, but you will use only once. So these are not rechargeable batteries. So this lithium battery, similar to this metal hydride battery, you will have similar to the other zinc carbon battery. So they are used only once and you throw them. And this is also known. So lithium has been known for some time, and these batteries also known for quite some time. Then what changed? What was that different which made this lithium a promising technology now? So as I said, the lead acid batteries was known for a long time. Even the electrical vehicles, I think this is about 1899. So people made cars. I think whatever the e-car we talk about, it was made much earlier. So people ride this electrical car. So this has a speed of about 105 kilometers per hour. I think that speed they can able to run. They made lead acid batteries. Was able to put in here, and he was able to run this cart, and they were selling this at that time. And coming to mobile phones, though we all of us has a very small mobile phone, they existed much earlier. This is about 1973, even much before I was born. Martin Cooper, the Motorola is again a telephone company. I think most of the people may know. So he made the first, or he demonstrated the first mobile phone. So this mobile phone was about 1.1 kg. So not the 100 grams we have now, it's about 1.1 kg is the weight of the battery he had. And he made a call at that time. So this, he has to charge for about 10 hours for a 30 minutes call. So you can speak for 30 minutes if you charge for 10 hours. And he's the head of the Motorola. So he called to his, I think his rivalry that time was, I don't know, Sony or somebody. I think he called to that head to say that, so we have developed a mobile phone in which I can talk to you. I think the first call he made was for his rivalry in terms of his business rivalry. And that's one known event, 1973. And the other event is, radio has been existing since early 1900s. So this person, so he made a car mounted radio telephone. Again, he used lead acid battery. So all this used lead acid battery because that was the easiest thing which was available that time. So he made this battery in this moving car, and then he had this radio set where he can able to communicate things. So these are, you can say that kind of things which existed, which was known, but things have changed since then. So in terms of technology as a mobile phone, it existed. In terms of an wireless technology also, it existed at that time. So then what changed, if you think about, it is something called as a energy density. How much you will get per kg of a material. So that is called as an energy density. Compared to the batteries, I think what we have now, the energy densities of these, let me skip this, let me show that. So the lead acid battery, what we have is somewhere here. That means if I have, so this number is about 40. If I have 1 kg of a battery, I can power a 40 watt bulb. So if you have a bulb which is 40 watt, you can power a 40 watt bulb for 1 hour. So that means 40 kilowatt hour per kg. So that's my energy density. And the same material, if I have a lithium ion metal, so I can get 200, that means at least 5 times higher than the lead acid battery. For the same amount, for the same 1 kg, so I can power at least 5 bulbs of 40 watt for 1 hour. So the amount has increased. The energy density is how much you have within the material, so that has increased. The quantity is same, the size is same, but the power what you get out of that is very, very high. So that we call as a energy density. And that is what changed. When you say higher energy density, the weight is also less. And lithium being the lightest material which is known, so that changed things. And compared to other material, they have low self-discharge. That means if you have a lead acid battery charge and if you don't use it for 1 hour or 1 year, and then again if you you try to use it, so it will give less power. So it has something called as a self-discharge. So the reaction can proceed by itself and it would have lost some of its value. Whereas the lithium ion battery doesn't have that self-discharge. It has a very slow self-discharge rate that even, I think there was a report, even after 30 years he tested his battery which he left it in his lab and he could still get the power out of it. So that has a power rating to hold the capacity even for 30 years. Okay. So those are certain advantages. So it is lightweight, you get high energy density, and you have very low self-discharge rate. So these make them lithium a promising material compared to the lead. So the other materials come here. So as I said, we have nickel cadmium, nickel metal hydride, so lithium ion. So this is how the progress made. So as you went higher and higher, your energy density is increased. There is a small difference here. Lithium metal itself can be used, and lithium ion, so I'll come back to that in a minute. So lithium by itself can be used as one of your material. If you have an anode and a cathode, you can use lithium as such as your anode. But what happens is there is a process called as electrodeposition. So any metal, if it's in a solution, you tend to deposit if you try to do an oxidation or a reduction. So the metal can grow, or in other words, it can grow over a period of, you are doing a charge discharge process, over a period of time the metal can grow, and so you have an anode and a cathode, and then there is a separator. It can go through the separator and touch your cathode. So that means there is a short circuit is possible. So if you put your positive and negative together, you always have a short circuit. So if you just use a lithium metal as such in a secondary battery, the lithium has a tendency to grow and there is a short circuit. So that will lead to fire. So that's the problem which is there. Though the energy density of a pure lithium metal is very, very high, people don't use lithium metal now. They use this lithium ion because of the safety reason. I'll come back to that in a minute. And yeah, suddenly I put a battery here, I think we're talking about science. So this is how the lithium ion battery work. It is like two badminton player shuttling the cork across. So that is how the principle behind which this work. So you have two people, I think PV Sindhu on one side and her opponent. So they try to shuttle this. So we have a shuttle effect. So the shuttlecock comes this side and she transfers that to the back. So that's what exactly happens in a lithium ion battery. You have an anode on one side, you have a cathode on one side. The lithium ion will shuttle between the anode and the cathode. So that's the working principle in which the lithium ion battery works, similar to the shuttle player, how they do. So if you look at, I think if you open a lithium ion battery, you will have an anode, you will have a cathode. On the anode side, so we have SF now, we have graphite as a material. Graphite has a layered structure. The graphite is the pencil. You know, if you have a pencil, the inside the pencil we have the graphite. So that if you look at the atomic scale, it has a graphitic structure, means it has a layered structure. It has some gaps between every layer of this graphite. And in this gaps, it looks like a arranged shelf. So this is a graphite. And on the other side, the lithium ion battery what we use today either you can use a lithium metal or a lithium cobalt oxide. I'll come back to that. So this has the ability to, so this is the lithium source. If we use a lithium metal, during charging, so this lithium will go to the graphite. So all the lithium will go this side. It's like the shuttle player sending the ball to another side. And during discharge, so they stay here, and during discharge they come back to this side. So the graphite will send the lithium ion back into the lithium metal. So this is how a battery will work. So you have a lithium metal, you have a graphite. During charging process, all the lithium will go from one side to another side, and during the discharge process, they will come back. Similar to what we see in here, how the shuttle goes in. So the lithium shuttle between these two. So that is why it is called as a lithium ion. The lithium ion is the ion which goes across these two. Whenever there is a lithium goes, there is an electron which goes on the other side in the circuit. So this flow of electron will get you the electrical current. The electrical current is from this one. And to get into that, so you have a positive electrode and a negative electrode. So similar to what I've shown here. So we have and so we need a current collector. Not only the electron should go, so you need to take that electron through some circuit or a collector. So we have a current collector here. So you take a metal in which you deposit this particular material. In this case, it's a lithium cobalt oxide. And you take another metal and then you deposit, let's say, graphite. And then you charge it. You need a separator because they should not touch each other. If they touch each other, then there will be a short circuit. So you have a separator. And you also need some ion movement. So that separator has an electrolyte. You put a small electrolyte in it, and in which you dissolve some lithium salt. So because that lithium salt will help you to transfer this lithium ion faster to other side. So the lithium ion will go. The ion will go from your anode or your cathode, and on the reverse side it will come back. So this is how the charging and discharging will happen. If you look at the chemical reaction, so lithium cobalt oxide will lose some lithium, so L1 minus X. So some lithium is lost, which is X lithium is coming out from this material, and this X lithium will go and get deposited on this carbon material, which is a graphite, and then you get LiXC6, so it forms this compound. So at the anode it will be 1, cathode it will be 1. So overall, if you look at the lithium cobalt oxide on one side, carbon on another side, so some lithium will come and sit on this one and you get X1. So during charging the lithium will go one side, during discharge the lithium will go back to its original position. So this is how the charge discharge process will happen, and this process is called as intercalation. So you allow the lithium to go and intercalate with this particular material. Okay, so it's called as you need an electrode of appropriate size to hold this lithium. Okay, so in case of this process, it can be, here somebody want to win, but here you don't want to win, but the ball should always shuttle. It should never, somebody should not lose, both should be winners. So if they are of different height, if they are different dimension, there could be a problem. If they are of the same height and same size, your ball will always go up and forth without any problem. That's why if you look at boxing, you have heavyweight, lightweight, and so on, because you wanted to have an equal dimension between two people. So that has to be matched here. So you need some material which has a very similar property that of your cathode, so that the lithium ion comes in, sits here, and then it goes back to the same place. And so in terms of materials, if you look at, so I have an anode and a cathode, which is this blue color is the electrolyte or a separator. So during charging process, all the lithium ions will go from here to here. So here I have a graphitic nature in which, so as I said, the graphitic layer has some holes or layers in which the lithium ion can sit. So here I have aluminum current collector. So aluminum is used as a current collector. On the other side I use copper, so you need some metal. A copper is used as a current collector, and you charge it. During discharging, whatever lithium we went that side will come back here and will occupy the side back into this particular thing. So this is the process in which charging and discharging happens. Okay. So this is the main context in which I'm going to explain to you in the next few slides what scientists have done. So this is the process in lithium ion battery. And so few things are needed. So there were a lot of research. So one important thing which we need is a separator. You need a material which separates the anode and the cathode, and you need a solvent. That solvent should be able to conduct your lithium ion. So the lithium ion should be transferred in that solvent. Because if it's a dry material, the ions cannot go. You need to have a wet material. That's why we are using a solvent in it. So if you look at, there are several membranes were used, separators. These are a lot of materials are there. It's nothing but it's like a plastic paper. You have a paper, that's your separator. So there are commercial materials are there. It's made of usually a polyethylene or a propylene or a polyethylene oxide. So a lot of materials are there. One of them you can choose. So you have an anode and a cathode. In between there is a separator. You soak the separator with an electrolyte. And this electrolyte also has some lithium. So choose the electrolyte. We have a lithium salt is again used as an addition to that electrolyte. So the one thing which revolutionized this is, because earlier I talked about lead acid battery, they use water in sulfuric acid as electrolyte. So water has a potential, if you go about 1.23 volt, your gas will evolve, hydrogen or oxygen will be evolved from two different places, or water will split. If you have H2O, if you have a very high voltage, your gas evolution will happen. It will not be stable. So that is an invention which was made. So you need an electrolyte. So lithium can give you up to 3 volt. So that means water cannot be used in lithium ion battery. Electrolyte which is stable is that potential window. You are going to 4 volt, 5 volt. Your electrolyte should not split or it should not decompose. So you need to choose an electrolyte. So that is where a lot of chemists worked on developing different electrolytes. So these are organic electrolytes, and also they should be conducting. Not an inert material, it should also conduct the ions. So dimethyl carbonate, ethylene carbonate. So these are some of the electrolyte which was produced that time. And to that you add a salt like lithium. This is a commonly used lithium hexafluorophosphate, LiPF6, or any of these salt. You add a salt which is containing lithium into this electrolyte. You dissolve it, and you use one of these separator, and then you take an anode and a cathode and put together, and everything is done in an inert atmosphere. That's how your battery will work. And that is where these three made a difference. So let me just start with the first one. So Professor Whittingham, so what he did, so as I said, so one side you have a metallic lithium, then you have a separator. So the electrolyte, the separator was, a lot of research was done, and then they obtained that. So he chose a cathode. So that time, so he made sure that a material should have a spacing in such a way that the lithium ion can come and sit here. So he chose a material called titanium disulfide. So it has a TiS2 is the structure. So this has a layered structure in which, so if you look at the charging process, so all the lithium ion, so this is the TiS2 material. So in this side you have a lithium. So during the charging process, all this lithium can go and then sit in between these layers. All these layers, so in between these layers the lithium can sit. So these lithium can go and sit in between these layers. This is a charging process, and the discharge process, the reverse happen. So this is his contribution. So earlier time this material was not known. So he made the first material, titanium disulfide. It has a layered structure which has a gap, or the gap which is equivalent to that of the lithium to come and sit here. If you have too small, too thick, then it may not even come back. So you need to have a right amount so that the lithium can go here and come back to this metal. So this was his contribution. So he developed this material as a addition to as a cathode. Then I told about this problem. So if you use here a metallic lithium, over a period of time it will grow because your lithium is going up and down, this lithium is going. So some will retain, and over a period of time, so the lithium will grow and it will pierce your electrolyte and then touch your cathode. So there will be a short circuit. So this is how it will grow. It will just grow like a dendrites or whiskers we call. So there will be short circuit will be there. So it will spoil your battery. And this is where if still it happens, then there will be a fire in your lithium battery. So this was a problem. That's why this technology, though he made his invention, it was not successful because this was a problem. And then a lot of research went on, and this Professor John Goodenough, so he thought that, so instead of having this material, why can't we change to some other material? And during this time, so he gave a better material than the lithium titanium disulfide. So he thought we will also have lithium in here. So he made this lithium cobalt oxide. So this material also has a very similar structure to earlier one. So it has this cobalt oxide in which the lithium can come and sit in here and then go back. So this has higher, so the earlier one had a little lower potential. The voltage of this was about only 2 volt. So he changed this material to lithium cobalt oxide. The anode was same, he changed the cathode. So he can get up to 4 volts. So the voltage was almost doubled. And this worked well. So it had higher what we call lifetime compared to the earlier one. So he used a propylene carbonate as a solvent, and then again lithium salt, everything was used. So he changed. So he changed the earlier titanium to lithium cobalt oxide to make it a higher voltage. And then this particular professor from Japan, Akira Hoshino, so he came into picture. So he addressed, because the earlier problem was the dendrites will grow and short circuit, so the battery will catch fire. So he wanted to avoid that problem. So he took the lithium cobalt oxide which the Professor John Goodenough developed. On the other side, he took, instead of lithium metal, he took just a pure carbon. So he took carbon as a material. Carbon was obtained from petroleum coke. Carbonaceous material. Carbon as a graphitic structure. The carbon which we use today was just thought by him. This side he took the John Goodenough material, this side he took carbon, and he got the same voltage. So earlier in this case it was a lithium metal, so he took carbon and then he used lithium cobalt oxide, and then he was able to get 4 volt, and here the short circuit problem was completely eliminated because this cannot grow, carbon will not grow, so only the lithium will shuttle between up and down. And this had a longer lifetime. There was no, the fire was completely avoided, there is no short circuiting, and then it has a longer life cycle compared to what Professor Goodenough was developing before. And he worked in a chemical industry. So the other two were university professors. So he was earlier, he was in a chemical company. So you know, any technology you develop, you need a partner industry to take that forward. So he was good enough since he was already in industry. So this, they were easily, they commercialized. So they can able to commercialize this much faster. And so this, he was able to get this product immediately onto the market. I think Japanese were, I think usually electronics, I think Japanese were way ahead of most of the people. So this was immediately put up for a commercial scale, and they started to sell this material. So these are the 3 contributions which 3 different people made, and this is what we are using today. This later changed. I think this was earlier he used just a carbon. Then after the discovery of graphene, people started to use graphene, or a graphite material. So graphite again has a layered structure. So you use graphene for your anode material, and cathode material. A lot of development happened. People started to replace some of them. So these are the different other materials. So this is the lithium cobalt oxide, which is a layered structure. So it looks like this, and the lithium can come and sit here. So they made this we call as a spinel structure, and this called olivine structure. So most of these again was developed in Professor Goodenough lab. So these are different forms of instead of the conventional this structure. So people tried to use various other structures, and some of them were successful, and some of them gave, depending on the application. So some gave higher stability, some gave higher power. So depending on the application, I think sometimes you need a very high current, and sometimes you need a current at a very slow phase. So they were able to develop these material to get different performance with these materials. So here it was, if you look at, it's a one dimension. So this is like your lithium can come and go in any direction. It's a kind of it can come in this direction, or also it can come in this direction. It's a 2-dimensional one. So this, the other structure is 3-dimension. So this particular one can come in the up, it can come in the side, it can come in the down, x, y, z, all direction it can come. It's a 3D material they call. And this kind of a thing, it's like a cup, or you have a closed environment. So only one direction it can come. So there are constraints to each of them, but I think people started to develop different materials just to make sure lithium comes and sit here and then go back. And in terms of capacity, so this lithium cobalt oxide has about 270 milliamp per hour per gram. That is, if you have a gram of material, you can get about 270 milliamps. So that's what it indicates. So these are the theoretical values, and then these are the practical values, what is people have obtained. So there are still constraints, and these are the voltages. You can get, I think, about 4 volt, I think 3.4 to 4 volt you can get with this cathode material. I think we're running little short of time. Let me, I'll skip few slides. Let me try to, I'll skip few things. So these are the development which happens. Okay. Okay. So people also now, batteries are used in every form. Also, the military is one area which people wanted to use. So they work in extreme conditions. Sometimes in very low temperatures. Sometimes they are in, if you are in Himalayas, or sometimes you are in a desert. So they have to work in different temperatures and so on. So people also look at replacing this that electrolyte. Whatever we talk about, the liquid electrolyte can be replaced by a solid electrolyte, or even ceramics. So people started to use solid ceramics. So people are working on that. So depending on, so the lithium ion battery was, so conventionally we use it at room temperature. I think these, in terms of comparison to lead acid battery, the lithium ion batteries can sustain higher temperature. Like it can work even at 50 degrees, it can work even at less than 0 degrees. So here people tend to go still further. So people have looked at different anode materials, different cathode materials, different electrolytes to improve its performance to work in extreme conditions. So that is an ongoing work which is still there in the research. And the one thing which is striking and has taken a great lead is the mobility, the transportation system. So this is, I think, Tesla. I think people might have heard this in the recent time. So it is, I think, as I said, even 200 years back, they drove a car with lead acid battery. But today it's the same car, but only the weight of that has reduced. So because of the reduction in the weight of the battery, they were able to run this for a longer time. This has a 100 kWh, and this can drive up to with a single charge about 580 kilometers in a city ride. So this is the drive range it can go as of now, Tesla. And it's expensive as of now, but I think anyway, if you think about the mobile phone calls, in earlier times we used to pay 20 rupees, and even the receiver would have to pay some few rupees to receive a call. So today it has come to less than a rupee or so per minute. So I think it's a time which decides, I think, how the amount has to come. But again, we are in the beginning of this EV vehicles. And Nissan is another company which have made this Nissan Leaf. So this is a SUV type car, and this is a family car which is affordable to everyone. They call it as a leading environmental friendly affordable car. It's a full charge, it can go to about 250 kilometers. And so these are currently, you can charge it in your house or in the office whenever it's not being used. And so these are other cars which are there in the market, which soon will come to India as well. And India also has a mission to look for the electrical vehicles. I think that was started, I think, earlier this year. I think they had approved goals for this mission. And e-rickshaws are also there. I think in IIT Madras we have a battery center where about 10 to 15 vehicles, e-rickshaws are there. So they take students and other people for free. I think it's in a kind of a pilot testing which is there. And we have also seen, I think recently, Tamil Nadu government and also Professor Modi, I think they all have their say for the electrical vehicles. So which is, again, it's at the beginning. But I'm sure, I think, if you think of 50 years from now, I think all our vehicles could run predominantly in electrical vehicles, and for which the lithium-ion battery will play a major role. Yeah, I think this is the end of my lecture. I think most of these materials were taken from the Royal Swedish Academy of Sciences, and some papers by the 3 Nobel laureates, and some images from the Google Images. And I thank you for your attention. Thank you. Yeah, so I think questions we can have it at the end. That would be better. So that will give some time for Aravind to speak.
Thank you, Raghuram Shetty. I'm sure all of you will have, at least many of the students will have questions, doubts. I myself have a couple of them. We'll wait. Next is Arvind Kumar Chandran from IIT Madras, same department. He will talk to us about, now we heard about lithium-ion batteries, the growth for which the price has been given, and what is it made up of, how do we get it. Now the next is, where do we go from here? In fact, already a lot of developments he himself mentioned, electric cars, etc. Now we use a lot of oil and gas and various other things which are environmentally not great things. So now the electric cars are also becoming popular, but unfortunately it's very expensive. So you will find as we go along, as he mentioned, it will become cheaper and cheaper. Now these electrical vehicles are likely to be used more and more publicly at the public sector level, buses, even trains, etc. will have some kind of a new mechanisms by which we are able to reach the next levels. Now, Arvind will talk to us about alternative to these things. Thank you.
So I think this is a bad thing to do. Someone got Nobel Prize for a topic, and I'm going to talk something opposite to it, right? It's going to be, there should be always a villain to make the hero quite famous, and that's what I'm going to do today. So Professor Raghuram Chetty gave a very nice introduction to batteries and lithium-ion technology, and I'm going to see and talk only in Indian context. And before that, we will see a bit of advertisement about my group. It's just to give a feel of what exactly we do in our lab at IIT Madras. And I could see some familiar faces sitting on the other side. So, and by the way, this is the first time I'm giving a talk to a very generic audience and general audience. So if at all you have any questions, if you think that I'm going too much technical, just throw something at me so that I'll stop and then I'll explain, because I don't see a reason. If you don't understand, I keep talking and then I'll make you to sleep. Good. Great. This is about my group. So we are a group in chemical engineering at IIT Madras. We work only on electrochemistry and photoelectrochemistry. This is in here. So Professor Raghuram Chetty works purely on all aspects of electrochemistry, starting from fundamentals to applications. In my group, we have added a photo to it. It means that we just add light to it and try to see what happens to that. So we also work on all sorts of fundamentals and all the way up to the applications. So my group started with this business right here, the solar cells. And then it moves like we also work more on how to store solar energy. One is batteries. I think all house inverters do have this lead acid batteries, and they die in 1 or 2 years, right? That's how, and then you have to keep replacing them once in a while. So there are other ways by which you can store the solar energy. One is you take water, split into hydrogen and oxygen, take the hydrogen and store it. And of course, you can use that to run fuel cells or whatever you want to. And that's our key research. This is still in a very fundamental stage, and we are doing a lot of fundamental work out there, starting from materials design to do the water splitting. And on the other side, me and Professor Raghuram Chetty's group work quite closely on this carbon dioxide reduction. You know, if you see the market, carbon dioxide is toxic, this, that, heck, and then pollution, health issues, everything is coming up. But if you look at the Indian forecasting, like energy forecast, and we are going to build more and more coal power plants, because you will complain if you don't have power in summer, probably in winter too, right? I think you will complain about government. But you don't want to increase the power price also. So are we going to move to something that's expensive? Obviously, the answer is no. So Indian government will keep investing money in power plants and will be emitting carbon dioxide. So the best option is now we use renewable energy to convert that carbon dioxide back to fuels and then use it for something meaningful. That's the direction that we are taking. And we are working quite extensively on that area of research as well. And you see that something which is not in any of these formats, this is in metal batteries. This is what we work on, and that's the topic that I'm going to discuss quite extensively. And we did not have this topic just because I like it or something. We judiciously put our efforts and try to see what is going to be the next technology after the lithium-ion batteries, or probably in parallel with the lithium-ion batteries. Being said that, if there are any lithium-ion battery lovers, including Raghu, don't get offended by it. Sometimes I may go harsh on lithium-ion batteries. Not too harsh though. Great. And any research that we do, beautifully funded by a bunch of government funding agencies, and I really thank them. Without those money, I think we wouldn't be in existence at all. So I really thank the great deal of funding agencies, starting from IIT Madras, literally you can imagine any funding agency, we have money for all of them. And that's my group. You have money, you keep it in a pocket, beautifully, safely, do nothing with it, because your interest will be earning in the bank. Of course, we need to have a great bunch of people with brilliant minds to working on it. I'm here just an ambassador of their results. That's it, as simple as this. So at least I could see one of our students that me and Raghu are advising is here, and this man here, Shivaram Prasad. I think, Shivaram, are you here in this picture? Oh yeah, this guy. He's sitting in that corner. Yes, great. So I should thank my students like the way I thank my funding agencies. They are assets. Good. What we do in our group, simple. We develop catalysts, test them, and then see how they perform in any application, and then learn if they don't work, why they don't work. Then we put our feedback loop back in, try to redesign, and then work on it. This is our group strategy, as simple as this. This is what we work on. And of course, it looks like when I showed our research arena of our group, it looks like we are working on a variety of topics, but only fundamental thing is we design materials and test their catalytic property, as simple as this. But then we put the catalyst in different places, different applications. So our core interest and expertise is electrochemistry. And you could see that we work on water splitting, carbon dioxide reduction, oxygen reduction reaction, and for various applications here, as shown in this place. I'm going to show something. This is our recent invention. This was serendipity. We are working on something, and we got a material that can emit white light. Like the LEDs that you see on the outside, white light, it's not a white light emitter. You have a blue LED onto which a material is coated, a phosphor. The blue LED is being absorbed by that phosphor, and that emits white light. In the whole world, there is like, honestly, there are only like roughly 10 materials which by themselves can emit the entire visible light. And we have one of them with us, and we own one of it. And that's a recent invention from our group. And the next thing, just to give a bit more of it. So in our, when we want to split water to generate hydrogen, we need to have a catalyst. So typical catalyst in an electrochemical system is platinum. But platinum do not absorb sunlight. I mean, it's not a semiconductor, it's a metal. To harvest sunlight, at the same time do water splitting, we need a semiconductor which absorbs entire sunlight, at the same time stable in water, and that can generate hydrogen. And one of my brilliant students, his name is Hamdan, he made a new material which is CS2PTI6. At the moment we do have platinum, which is very expensive. But this material is stable in all pH. You can take anything, you can put this material in any pH, extreme acidic, extreme basic. This guy is damn stable, and they perform extremely well in terms of catalytic property, which at the moment we tested for 100 cycles of catalytic run to generate hydrogen, and it seemed to be stable. And this is one other invention. By the way, the iron oxide, the rust, whenever you see a rust in the flagpoles and everything, don't blame them. They are really nice material, and they are the ones we use to generate hydrogen and oxygen in our laboratory. Thing is that you cannot just randomly take rust from flagpole and then use it. So we have a size tuning, we have a morphology tuning and everything, and this is just a rust. That we made it look nice. Next time when you have a rusting iron, guys, don't blame it. It's a heaven. Maybe you will not see. That will be very more expensive in future. So we work on that as well to generate hydrogen and oxygen. And we also work with Indian Space Research Organization. We are not just only on fundamentals, we are also very serious in making products. And one of our flagship projects is we are making solar panels for low orbit satellites for ISRO. So we work quite closely with Vikram Sarabhai Space Center and Baba Atomic Research Center, so to develop these solar panels. So we work, like our spectrum ranges from very fundamentals about how electrons travel as soon as you shine light onto material to all the way up to the product. Our group works in all the spectrum of research. And of course, we cannot do anything best compared to the biological systems. Take a photosynthetic microorganisms. They mastered the technology. You take them, you shine light, and they convert into carbohydrates. The only thing is that we have some part of the technology, but they typically will not give electrons out of the system. You take a microbe, any photosynthetic system, leaves like green leaves, you shine light, it will be absorbed in the chlorophyll, and holes will be transferred, and eventually some carbohydrates will be made within the cell. That electron will not come out of the cell wall. And we have a very nice research partner in Switzerland at École Polytechnique Federale de Lausanne. It's Swiss Federal Institute. What she is doing is, there is a protein which is hindering the charge transport. She is trying to pull that protein out, which is hindering the charge transport through the cell wall. And in our lab, we are trying to see, after removing the protein, if the electrons within the cell can come out of the cell. So it's a very multidisciplinary project. So it's more like this. I can give an example. You may be capable of doing everything. Like for example, I take if you're organizing a marriage ceremony, you can arrange chairs, you can also wash dishes, you can also serve, you can also be at the reception to do things, but you cannot do everything in a marriage reception, right? You need people to work on it, and that's our strategy. It looks like sometimes you work with many people, but you have to be clear in getting right people together. Fortunately, I have Raghu also with me on board, and this is one of our projects. And you know, by the way, we like differentiated between respiration and photosynthesis. One of my students made a very nice experimental setup to differentiate the electrons coming out of the cell because of respiration, because of photosynthesis. So we worked that out. So these are the key results. Being said that, we'll go into the real topic of today. So these are various batteries that Professor Guram also showed. And I want to ask one thing. How many of you have seen this or at least heard about this specific battery, the one here? Anyone? Great. Sir, please. Pacemaker. Imagine you're allowed, your mobile phone battery can fail, right? They're allowed to fail. If it fails, you just throw it out. I think the present is, of course, you have to break the battery open. So 7, 8 years back, we had a privilege. We just had a cover at the back side of the battery. We can open it, replace the battery. Now the present day mobile phones, in the name of safety, for whatever reasons, right? So this specific system, you cannot fail. I think I'm on the right side. You cannot, this batteries cannot fail. Otherwise, you'll have to cut open your, put one more, take the old one out. By the time, person may also be dead. So the critical part of it, there are some batteries which are not really that critical, and some batteries on the other side which are extremely critical. The chances of failure have to be zero, literally zero, and those are the things. So batteries is not just like a 2 electrode and a membrane. Like Raghu pointed out, you have to do something in a very inner way, like if you want to work with these kind of batteries, they have to be tested million times before they go into someone's heart. Otherwise, they will not deliver electric pulses to your heart and patient will be dead. So it's just to give you a feel of like the range of critical thinking that we have to put in to design a battery. It's not very simple the way we might think. Next, I don't want to really do this. I'm going to skip that. I just want to show this one. This is a slightly modified version of what Raghu has shown. So typically, you take like 2 levels. Let's say you have a tank there and you want to flow water down. Your tank is situated there, like your house syntax tank or whatever tank you may have, water flow downhill, right? Same concept is being followed in the lithium ion. When you need to discharge a battery, the energy of electrons will be above, and then the electrons that is in the receiving condition, a metal that's receiving the electron, the lithium cobalt oxide for example, or titanium sulfide, they'll be receiving the electrons. It has to be like this, it has to be positioned like this. If it moves like this and then you do like this way, electrons, it's like discharge. You have to charge it. You have to give energy so that you push it manually by electric power or voltage, and then you try to do the charging. So what ideally we would need is, this is like vacuum level. So if you are a physicist, you like vacuum scale. If you are a chemist, you like energy scale. You know, this is the biggest difficulty. If you read a paper, sometimes you will have both these scales. People say -2 volts versus NHE, and then sometimes you ignore that NHE. And if a physicist write a paper, they will use, what is the equivalent of -2? -2.5. And then you'll be confused. Both the guys might be speaking the same language. It's just about terminology, energy or vacuum. So when you read a battery paper, please be very cautious about it. Either you speak about energy scale or some other reference scales are also there. So essentially what I would like is, above this 0 or -, electrons are free. So you cannot, there is no material. You have to just knock the electron off, like in many systems. So you have to have your anode, for example, during discharge, negative electrode at this position, and then positive electrode as low as possible, so that you will get the maximum possible voltage in a system, right? So that's more like water from the tank up is flowing the water downhill. It's MGH, like the potential energy you gain. Here it's the same analogy applies here. Now, the negative electrode should have a potential more and more close to the vacuum scale, I mean the -4.5, and the positive ones will have to be as down as possible. So the lithium ion is positioned somewhere right here, -3.5. Lithium ion, -3.5. And then their positive electrode is positioned somewhere right here, somewhere this position. That's why you'll get like 3.5 volts in most of your lithium ion batteries. If you take some other batteries, so for example zinc, it won't be here, it will be somewhere down here. So the actual voltage that you'll get will be 1. So it's just about where you position the tank, and tank full of water and the energy of the water. It's the same analogy. Great. Let's take a simple example. Probably I'll just skip quickly after this, because this is something that Raghu pointed out already. We'll take zinc and chlorine. This is a funny example, guys. Chlorine, I think no one would want to use it. You don't want to kill yourself, I'm sure. So zinc has -0.76 versus NHE. That's the potential of electrons of zinc, and chlorine has 1.36. It means in this scale, this is zinc and that is chlorine. So that's the voltage you get. So you take your battery. I think, as I said, you don't have a privilege to see what's the battery inside unless you go to a mobile mechanic, rip open that, and he'll give you the old crappy one. Then you try to find out what is there. There'll be something written, straight line, a dotted line below, and it will be written 3.6 volts. And that 3.6 volts actually difference between these. Of course, in lithium, this red will be slightly above. And maybe you might have noticed something. I'm going to skip that. So this is also something that Raghu pointed out. So when you buy a battery, how many of you noticed that something called mobile is if you buy MI batteries, like 2 years before MI batteries, the hot pants. So they'll have like 5,000 milliampere hours. Have you ever noticed that? 5,000. And then if you buy a lower version of it, not with the touchpad ones, with the standard keys, it will be like 800. So have you ever wondered what that number really means? So we'll see that here. For example, this is a simple formula you have to work with. For example, lithium can give 1 electron. So lithium atomic weight is 7. So 7 grams of lithium can give 1 mole of electrons out. Now, I'll take calcium for example here. Calcium is 40 grams and calcium can give 2 electrons though. But then 40 grams can give 2 moles of electrons. So now you will see appreciate what lithium can do. 14 grams of lithium can give 2 moles of electrons, whereas calcium, which is capable of also giving 2 electrons, needs 40 grams for that. So that's why lithium is the lightest and at the same time you can extract more electrons. So you plug in this formula, you get some number out there. You see that this is the number that you get typically. Milliampere hour, 5,000 milliampere hour in a battery literally is this. Of course guys, this is actual exact calculation of lithium, but in your battery you have battery packing and all those things, so they'll be taken into account. So here per gram is there, but there it won't be per gram. So you see that lithium is extremely high compared to calcium. Of course, hydrogen is very high. Hydrogen is extremely high, but the problem is per gram of hydrogen you will get high capacity. We call that as a specific capacity. However, per liter of lithium, the amount of how many grams of hydrogen you can store, that's fairly little. So obviously you'll have to carry a tank along with you when you want to use hydrogen as an electrode, right? Great. So I just want to show the present day batteries. This is the actual capacity, the commercial batteries. Per kilogram of lithium ion battery will give somewhere around 140 ampere hour. And the electric vehicle era has come in and we have like huge requirements, and you'll see the requirements. This is from Niti Aayog. If you have time, have a look at it. Niti Aayog is really a good think tank. I don't know how it was before, but the present Niti Aayog is really good, and they give what is the roadmap for the electric vehicles and literally for all technologies. By 2022, you need to have 10 gigawatt hour of giga 10 to the power 9. Giga 10 to the power 9. I'll just try to compare this number here. This is an ampere. Typical lithium ion will give, let's say 2 volts. This will be roughly 140, 280, 480, 420, roughly 450. This will be 450 watt hour if I convert that to watt. 450 watt hour per kilogram of lithium. And now I need 10 gigawatt hour, 10 into 10 to the power 9. So you can calculate the amount of lithium that's required. And I'll show something very shocking in the next slide. And by 2025, India has a plan to, they have given a roadmap. If you want to convert many vehicles to electric vehicles, it has to be 50 gigawatt. So I think this is where the problem starts, and this is where we're going to stumble upon. I'll speak about it in a bit. And the cost of lithium ion battery. So I don't know if you ever seen a battery bus running around. There was bus number 1 from Central to Thiruvanmiyur. Bus number 1 if I A1, yeah. And have you seen a battery vehicle? There was some answer. Have you seen a battery vehicle running like 6 months ago? Ashok Leyland? You know the cost of a bus? See the standard bus? Any answer? 20 lakhs? You know what is the cost of battery bus that we have at the moment? Any guess? 1.2 crores. 1.2 crores, and they don't last long also for a few reasons. Of course, the technology will evolve over time, and they'll be like, initially it will be quite expensive, but are we ready to invest in that is one question. And the next thing is, do we have resources to sustain that electric vehicle, like continued lithium usage? And that is the second question. And one of the questions that you have to answer is the cost. At the moment, lithium per dollar, like in 2010 it was $1,000 per kilowatt hour. In 2016 it's $273. And the present day lithium ion cost, like lithium cost per kilowatt hour. Per kilowatt hour is exactly equal to the unit that your meter runs. If your meter runs 1 unit, we call, it means 1 kilowatt hour, right? That's what it is. And present day ones, it's somewhere around 210 to 270 buy. For example, the companies which are making e-buses, they don't make so many. They'll make only small quantities. Import them from China, so that will cost like 270. And if they are making batteries in-house for companies like Tesla, which is planning for a gigafactory, it will be somewhere around 210 to 220. So you'll have a $50. And however, there is a projection on what is the cost. So as you go down further, like in 2030, they projected that it may go down some company, like Niti Aayog including and Rocky Mountain Institute, they predicted that it may go to $60 to $67 per kilowatt hour. $60 to $67 per kilowatt hour. And some thing predicted like in 2025 it will be somewhere around 100. And I'll say, so in the Raghu's presentation he showed Tesla battery with 100 kilowatt hour cost. You just now calculate the cost of it. 100 kilowatt hour multiplied by that, whatever the cost per kilowatt hour, that accounts for the 30% of the overall vehicle cost. Then you multiply that by 2 by 3. Then that will be the actual price of your vehicle. So you will not buy. Indian market has done Mahindra Verito Electric, and they're very clever. They don't give you 100 kilowatt hour system batteries, which will be quite heavy, and they'll give you literally one. You drive from one end of Chennai, you're stuck in the traffic, you keep your AC on, you're forever stuck in the same place. Okay, that's one thing. Of course, you say that I want to pay only 10 lakhs and you want to get more, I think Mahindra cannot give also. That's another issue. So the test Mahindra Electric Verito model has somewhere around 18 kilowatt hour is the maximum. Whereas the BMW successful model i3, which is somewhere vary between, like depending on the versions, it can go somewhere between 18 and 42. Tesla, this is the highest one when I made, and Tesla Model 3 can go up to 75. The Model 100, right? Is that what you're sure? Model 100. That goes up to 100 kilowatt hour. Maybe that 100 is from the kilowatt hour of battery. And if you want to convert all the electric vehicles in India by a battery vehicle, you will need 2,400 gigawatt hour to 3,500 gigawatt hour. And this is going to be the biggest problem for this reason here. These are the elements here that's used for making lithium batteries. I'll show something, watch closely. Like you can see anything, the round which is not filled is the actual resource. The one that is filled is what is actually being planned to tap, or they're already tapping. Look at India, no lithium, no cobalt, no nickel, no copper. I mean, of course, there is small amount of copper. So what are we going to do? Are we going to keep importing? Great. We will move from crude oil to lithium and nickel. And the next big problem, after all these things, can we recycle it? There is no technology at the moment. Raghu's group is working on it at the moment. So getting selectively the lithium back is the biggest challenge, and we don't have technology yet that can be commercially viable. So this is one of the primary reasons why I think personally we'll have to try to see what are all the resources available within India and try to develop a technology that is local. So we always think Europe did it, so I'm going to do it. America did it, so I'm going to do it. Great, you can do it, provided if that fits your needs. So you always don't have to go to what they do. Next thing, I'm sorry. This is the battery manufacturing thing. You can see, you can have a look at it. California, that's almost the entire gigafactory is taking it. These are the manufacturing areas in California and Eastern America. And here, this is Korea, Japan, China. And India, nothing. We are not making any lithium-ion batteries. The reason we don't have a technology. And we'll keep importing technology all the time. That's going to be quite expensive. So this is one of the reasons why I think we'll have to tap some of the new technologies or try to develop something new. And we have a big challenge ahead of us to do that. And if we do that, I think we are in the big business. Next, safety. Safety is some big concern. So Tesla vehicle is made for US market. You go and stand in the middle of midsummer, in the midday in Madhya Kailash signal, you will know what heat is. Honestly, I'm not kidding. I was living in Taramani for some time. I go for lunch. There is a bridge, railway bridge on the top. I used to stay in the shadow. I won't even go on. Stand next to the park my bike next to the signal line. I'll stay like 100 meters away from it. And you take your battery out there, you put it there, it will boil, it will explode, and Madhya Kailash will be beautifully bright because of burning the batteries. So, like what I'm anticipating all these issues actually. So I'm anticipating all these issues to come up. This is the actual thing that happened like 3-4 months ago. It's a Tesla Model 3 vehicle. It was a vehicle parked. It's some Hollywood actor's car actually. You can search it. It just caught fire just by itself for no reason. And you know what they do like in battery vehicles? 15% to 30% of the energy generated by the battery is used to cool the battery itself. And now that is for not Indian condition. That's for wherever the battery is being made. Now you go and stand in the middle of in the midday, in Madhya Kailash, and now that 15 to 30 will become 30 to 60. So obviously whatever you spend in charging will be used to cool the battery itself down. So this is another problem that I feel probably we'll have to address. If you want to use how many of you felt the battery getting hot? Like your mobile phone, you try to use all possible, keep Wi-Fi on, full brightness, audio, every heck, and then you'll see the battery getting very hot. That is doable, you can cool it down as long as it's small. But if it's too big, there'll be a thermal runaway and explosion. And this is one of the reasons why I think we have to look for alternate technologies which may be safe. Being said all these things, still lithium-ion battery is the best. There is no alternative at the moment. And let me just quickly look into what are the resources we have. I know what are the technologies alternate to lithium that's available. So I'm going to present 3 different metals or elements that's available in India, way in excess that potentially we can tap. One is zinc. You see that India has somewhere around here. So you can look at all these things from Wikipedia and any geology survey maps. So India has a lot of zinc. Next, India has a lot of iron here. Next, this is bauxite actually, aluminum resource map. This is not actual map. India has a lot of aluminum also. So actually India is one of top 5 producers in aluminum. So we have all these 3 things. Can we use any of these 3 to make a battery? If there is any technology that is existing already that can come close to using any of these 3 materials. And that's where come in the metal air batteries. And we did a good survey. I have a very nice student, his name is Akhil. And he and him, we spent like several hours brainstorming, and we literally dug out all the existing technologies. And then we came to a conclusion, very strong conclusion, that metal air batteries can potentially be a complement to lithium ion or can surpass lithium ion. Being said that, the existing metal air batteries are not up to the mark to be put in any vehicles. So we have a lot of challenges to solve, and that's where we are there at IIT Madras. So typical metal air batteries, we'll have any metal. That metal can be iron, aluminum, or zinc, one of the 3 that we have well in excess. And the other one is oxygen. You just take oxygen from the atmosphere and use it. Of course, it looks that guy, which is really the most killing guy of the entire device. So how to really use it? So what you do is, you take a metal, you oxidize it, take electrons out, and then you use those electrons to reduce oxygen to hydroxide. It means water. So this is what we essentially do in metal air batteries. And here, I would like to see, just look at all these 3 here. Don't look at the other things. There are 2 things here, specific energy, which is like the size of the tank. I'll give 2 terms, specific power and specific energy. Let's say I have a 200 liters tank, and one has 1 mm diameter outlet, and the other one has 1 feet diameter outlet. Tank size is same, 100 liters. It means the energy of both of them is same, and that is exactly what I mean by the specific energy here. Then, how much of that energy can we take out in a given time? That says what power that a battery can deliver. If the tank outlet is larger, we can take more water out of it. It means that high power system, the same thing. So lithium can give high power, metal air batteries cannot do that. So that's what we're going to look into quickly. Just look into these 3. You can see that the values here, you have to believe me for now, are very much comparable to lithium ion batteries. I'll show one more plot. I think that'll be, I'll come here and just give me a second. I'll come here for a second and then I'll go back. So this is that specific energy, size of the tank, right? Here is lithium ion. And here is zinc air battery. You see that they are comparable, right? In fact, more than that. So zinc air has a great potential. Now, let me look on the other side. I'll take one more step here. Yes. Here. How much of that I can draw in a given time? The size of the outlet. Here you see that lithium is excellent, and you see that zinc air is too bad. So if you stop your vehicle in the traffic signal, it will not start. Someone has to push. If it starts moving, zinc air will start giving the energy. So that's the biggest problem we have to address now. That is one of the research that we are working on in our group. I'll go back and slowly say how the lithium zinc air battery works. So it's just the reason why I selected zinc is the technology is more mature compared to aluminum or iron air batteries. If you need more information, talk to me. So we have a zinc electrode, just a simple zinc metal, and then we have a cathode which is porous, so it can take oxygen and convert that to hydroxide. And we have a separator in between. And we have aqueous electrolyte, which means based on water. Typically we use a oxide dissolved in water. That is, commercial batteries also do have that. So we can address the issue of safety, we can address local issue, that is stability of zinc. The only thing is the device long. So we will discuss what are those parameters. So how does it work? As simple as this. You can take a metal contact and you print zinc. So you can take any metal and then you print zinc onto it, or you paste some zinc onto it. So zinc will oxidize and then give electrons out. Your battery will take electrons out. On the other side, you will have a 3 combination of system in the second electrode where oxygen is getting reduced. So we will have a very porous layer which is hydrophobic, which means the electrolyte is aqueous. If it's hydrophilic, that will come out, it will leak. So it will be hydrophilic. And at the same time, it will not let any water vapors from outside to go in. So we take oxygen in, and that's a porous current collector, and we have a catalyst coated on carbon. So at the place where this oxygen comes in, and then the electron from here comes in, and then at the contact with the electrolyte, you will convert the oxygen to hydroxide, and then device will give its current and potential. Okay, and this is something I just discussed in a bit. So now I want to see like where we are at the moment in terms of, this is the same plot showed. This is the tank outlet size, valve size, and this is the overall tank size. So the conventional lead acid batteries are here. The tank size is also low, and how much you can take out of the tank is also low. Here, lithium ion, the tank size is very high. At the same time, how much, this is in log scale. Imagine if I put it in the linear scale, you will see the actual difference like of the how good the lithium ion batteries are. Metal air batteries are somewhere right in this zone, right here. Like, or like probably can go right here also, metal air batteries. The commercial ones are here, and the lab scale ones are somewhere right here. We want to push that all the way up to the top in order to compete with lithium ion. What is ideally expected? I have full tank of water. If I need to take all tank of water in one go, I should be able to take all out of it. That's the way we have to design system, but in reality, it's not going to work out at all. Great. So this is the cost comparison. This is just a prediction. It may be, this is again for US road conditions. In India, we don't have such predictions. If you want more, you can read this paper in Nature Energy. So you see that is the cost of the vehicle as against the driving range. You see that this is the cost of the lithium ion of the commercial ones. And zinc air is this one here, the light blue one, the sky blue ones here. So it is at the lower end of the lithium ion. It is at the lower end of lithium ion. In terms of cost, even though the zinc is not mature and there is no mass production of zinc air batteries like the way we do for lithium ion, it is expected that the cost of zinc air will be far less than the conventional lithium ion batteries. And it is projected that zinc air battery can go to less than $10 per kilowatt hour already. As of now, the lithium is 250 on average, and it is predicted that it's just zinc, whereas the other electrode is just typically made of platinum also. Sometimes we will have few milligrams of platinum in the second electrode, which is another big issue, which I will highlight in a minute. And the cost can be very less. Obviously, it can really over the future of the energy market, EV market. And the other thing, we have zinc abundance. So you see that there is 300 times more zinc resource across the world compared to the lithium. And we have very good technology to convert that zinc that is back to zinc oxide. We have, like India has a technology for that. So once you spend the zinc to the zinc oxide or something, you discard the battery, they have a good way to recover the zinc oxide back to zinc. We have the technology, and it's commercially being used in many companies. And this can be fabricated in normal atmosphere. You can do it on your like table. You don't need to do it like sodium ion batteries where you catch fire if you try to do that fabrication in the normal atmosphere. And next, the problem, as I said, if you want to go for electrically recharged metal air battery like zinc, like lithium, when you try to discharge the battery, zinc will get converted to zinc hydroxide, and then it will dissolve in the electrolyte. When you try to charge it, they'll have to go back, and then zinc has to grow on the negative electrode. But instead of growing on the plate, it will start growing like needles, and this will poke, and then it will kill the battery. Although it won't explode, like in the case of lithium ion, because it is water, it won't explode. It will have a thermal runaway, no explosion will happen. So this is the place I think where we'll work on how to avoid that dendritic growth in zinc. That is one of the biggest challenges that we'll have to address in the coming future. That's what I've said. So there are some suggestions. Of course, you don't have to take that. That's based on my logical thinking and what I pursued to be the potential solutions, but we can skip that. Next one, oxygen reduction catalyst. For example, you reduce oxygen and you evolve oxygen during charging and discharging. So the catalyst at the moment is based on platinum. So you will have roughly 1 milligram of platinum per centimeter square. Although that's like too little amount, but we want to get away with platinum. So in my group, we are working quite extensively on doped carbons, and we found, one of my students found the carbon material that we made, metal doped, nitrogen doped carbon, was much better than platinum actually. So we found it, but of course we have their efficacy in the long run, how they do. So if you try to avoid those two problems, I think metal air batteries can come out and do a big job. But there is alternate option. Imagine I have a battery where I spend all the zinc. I have a holder, I pull all the zinc out as zinc oxide, I put a new cassette in, all of zinc. It's like petrol bunk. You don't have to wait for 8 hours to charge a battery. You take a battery out, you pull, the handle will be there, take all the zinc out. So there will be series of batteries, right? In a lead acid battery, you will see if you have 12 volts, you will have a 6 series batteries inside. So let's say if you have like all the negative electrodes connected to a common handle, after you discharge the battery, you hold that handle, take it out, put a new one in, and then that one goes to a centralized location for recycling the zinc oxide back to zinc. No, that's a fantastic idea, and that's what we are pitching in, and we are working closely with Ashok Leyland to deliver battery for them in next 3 years. So we will most probably will have a technology next 3 years. See, of course, when we start investigating something, we may run into trouble. As of now, for few reasons, we think this is going to work out. For unknown reasons, we may get ditched also. Next thing is, this can be charged very fast. If you do mechanical charging, it's very fast. You don't have to wait for 8 hours or something to really charge it. Of course, you can see the industry which sell electric vehicles, they say you can charge it in 2 hours. 2 hours. The energy that you spend to cool the batteries, this is insider information from Ashok Leyland, is more than 30%. So obviously, your meter runs 100 units, 30 units went to cool the battery, and only 70 units is stored in the battery. So be very cautious about that. Great. So I'm going to skip that one as well. The other minor problems about basic design. For example, the carbon dioxide in the atmosphere, like that's there. We have a lot of carbon dioxide in the atmosphere, which can go into along with the oxygen and can form carbonates and clog the pores. So any air that's getting pumped into the battery has to be filtered first for dioxide. I think that filter has to be. Those are very minor problems. It's not something really big that we can solve. And of course, how to replace those cassettes in a very fast manner. Like you just have to give like 30 seconds to replace it. Like we have to prove that. Like we have that target in our group. So I'm just giving you a battery pack. You have 30 seconds. That one out, put the new one in, and then ready for operation. It's not as fast as the way I did with the nothing in the virtual battery. We'll have to have a real battery with us to execute that operation. And the next thing is that, anyway, this is like we have the technology. The reason why I said problem, after you take zinc, convert to zinc oxide, one thing is you can use sunlight in your local locations and can do electrolysis, convert the zinc oxide back to zinc. That can be done. Alternatively, it can be sent to a central location where zinc oxide can be converted to zinc. So these are two things. And by the way, if someone says these are clean and neat, just ask the question, where is the power coming from? Power is coming from coal power plants. Instead of emitting carbon dioxide everywhere, you're emitting in one place. As simple as this. So there are a few reasons. So eventually, I mean, it's not a problem actually at the moment. These are the things that you have to address. There is nothing to laugh at this one. So we have to go to complete wind or solar related conversion of the, like our charging the batteries. That's the way I think our Indian market has to go. And already we have enough power cut in summer. And the vehicles in Chennai becomes EVs. Like for sure you will have a 16 hours power cut. I can guarantee that at this point of time. I mean, of course, we cannot blame those guys in the power plants also. They are just doing what they are being instructed to do. Next, guys, this is an interesting thing. It's an Israeli company, it's called Electric Vehicles. They ran a bus based on zinc air battery that was long back in 1999. Of course, we have funding at the time, so they ceased the operation. So what we did is, we learned the problems those guys faced. In fact, we talked to those company guys. We don't want to reinvent the wheel. When you have a wheel, we try to see how we can improve it. So we don't want to say that I will start from scratch because I'm Indian guy. I want to develop indigenous technology. That's a stupid thing that anyone could ever do. So we started with what is existing and then try to see what are the problems they faced and try to improve on that so that we get a better technology. So we don't have to spend few years to do the same thing, whatever these guys did, like 2.5 decades ago. So we got all the finer details from this company. Next. The second technology, apart from metal air, is redox flow batteries. Redox has a large project on redox flow batteries. So where, this is for large stationary storage. You have sunlight everywhere, but you need batteries to use them, right? That's the biggest problem. So those batteries will keep increasing in size. For example, you have a solar farm somewhere in the middle of desert or something. Like if you have a 1 megawatt plant or 5 megawatt plant or 100 megawatt, are you going to use batteries to store all the energy? Then I think the cost of batteries will be much higher than the energy that you can get. Rather you burn coal and get the energy. It's as simple as this. So that's where the redox flow batteries are coming in. What I'm going to do is just you feel that redox flow is also a potential technology. And, I'm not going to explain all these things here, but one thing I would just like to highlight is redox flow uses vanadium. India has vanadium as its resource. So this is also a potential technology that we can consider for the future of batteries, in the future of batteries. Being said that, I just want to give few information about research. This has nothing to do with batteries. For someone who thinks that you take a flight, you cross Indian border, you have all the facilities outside. Within India, there is nothing. If you have that thought process, I'll give you something. I worked in world's best labs, and whatever the facilities, University of California, Berkeley, I don't know how many of you are aware of it. It has 77 Nobel laureates, one institute. And the facilities I had when I was a postdoc is much less than what I have in my lab at IIT Madras. So, never ever, this is something I come out to, never ever complain that India doesn't have money, India doesn't have research. We have great facilities out here. It's just you have to go and talk to the right people. Come out and talk to us. So, if you be inside IIT Madras campus, visit our lab. So, 3 people from TNS have visited our labs, and I'm sure I think they didn't get a chance to really know what each and every machine can do. So, we have great bunch of facilities. Some of them are in-house built, some of them were imported, some of them were built by the companies in India. So, everything happened. Next. This thing, don't try to be very conservative and be in the closed loop, guys. As I said before, you might be able to wash dishes, you might be able to cook, you might also be able to arrange chairs in a marriage ceremony, you may be also be standing in the reception. But remember, you need to have a lot of people to do the work if you want to execute something in a very short time. Guys, this is a great analogy. Of course, not for senior people, only for students, guys. Don't take others don't take it seriously. Spend time with members outside your close circle where you always watch TV, eat chips, go out and then talk to them. You may get some different ideas, and then they may give you different vision, like the way you came in here now today to get a different opinion about research. It's the same thing, but applied to research. If you are a physicist, I will only talk to physicists. I don't care about this chemist. No. And then I've seen many people talking, physicists are the best in the world, chemists are the best in the world, mathematicians are the best in the world. Ask them if any product that came out in the market, honestly the answer is no. So you need everyone to work on it. So talk to other guys. I'm going to show one great example here. The crystal structure of DNA, double helix. How they solved? There are 3 guys worked on it, right? The 3rd guy, you can read this book. There was a guy having a coffee. This guy, Maurice Morton, is one of the 3 guys got the Watson Crick, Maurice Morton. The idea of helical structure, he got it from a physicist in his group. He was just chat, and then that guy said, this diffraction pattern looks like it may be a helical structure. That was the hook that he got onto and got Nobel Prize. Guys, not all the ideas may lead to Nobel Prize. It may lead to somewhere. So remember, that's the line. It's written here in his book. So talk to people, go for coffee quite often, as much as you could, and discuss, not just gossip about science. Great. And I'm going to show you something here. This is about the marriage thing, guys. This is true in science. This is to show you a series of papers. Just like 5 seconds each for next 10 slides. And notice only one thing here. This list of authors. These are all the articles came out in Nature or 2 journals which are really highly reputed in the scientific community. Those are really revolutionizing science. Only those revolutionizing science come into those journals for all the grad students, if at all there is some here. You see the list of people and then the number of universities participated to invent something. 1, 2, 3, 4, 5, 6. See the number of people, probably it's less here, number of universities. So I lost the count. So, if you want to invent something new in this era, consider yourselves to in a research group. If you are a PhD student or a master's researcher, or if you're a graduate researcher, talk to people outside. You don't know when ideas will come out. And that's why I strongly recommend people, and then in my group we go for coffee every now and then, we party now and then, so that we get a lot of nice things. Guys, it's really true. It will really help a lot. Great, next thing, listen to others. This is the case. Sometimes my undergrads gives the best idea than what I could think of, what my postdoc could think of. So in our lab, we kill that hierarchy all the time. So there is no such thing called hierarchy. Someone can criticize you, no, not you personally, your research, you. That's the kind of thing we have in our group. So those talk to the people, talk about your research or anything, even to the junior people, they may come out with generic questions that you might not have addressed or not have thought of even. So there are many such things happened in my group. That's why I put this one, negative thoughts. So this is something, guys, if you don't talk about your research to community outside your group, you're dead. No facility in the institute. This is the most useless comment I ever got from anyone in the IIT campus. They said, we don't have anything. You come to the road, you go to, I don't want to say universities, we have everything. They come back with nothing. And I say that I have much more than. One of my PhD students went to Switzerland, very big institute. He said, he calls me, boss, this is how he said. He exactly said the same thing. So, they come to us, we will show what we have. He just calls me like boss, actually. So, Dhananjay, you know? Shivaram, you know Dhananjay? You remember him? Yes. So, you can talk to him. How that guy said, boss, that's how he exactly said the same statement. Good. These are some of the facilities I'm showing, like in single lab. You can look at it. And done. Thanks. Sir, maybe you also want to come out here.
Thank you very much, Arvind, for this enlightening talk. I should probably tell him, since I was trained in physics, theoretical physics, that too, we used to wonder about a great physicist, Paul Dirac. He wrote this equation, which later became known as Dirac equation for electron. And he said this equation will explain all of chemistry and most of physics. So that is the level at which some of the physicists used to talk, and later it proved to be a wholly incorrect statement. Anyhow, we as scientists, or many people, we always love to interact with other groups and learn from other groups and also tell to other groups, so that this interaction, multidisciplinary, interdisciplinary activities help in making progress. And it is helping even now. I never knew anything about computation and other activities. Now I try to learn what is known as machine learning and deep learning, and that too applied to some astrophysics problems. So there are very interesting issues which can come up again and again. So we should be prepared for changes which are taking place. Now I'm going to stop now. The floor is open for questions. Okay? And before all of you, any of you want to ask questions, just raise your hand. Probably it may be a good idea to tell where are you from, so that others know, and you can ask the questions so that we can get various questions. Now we know in lithium-ion batteries, they say some 1,000 cycles, 3,000 cycles. What fixes that kind of numbers? How many times it can go up and down?
So I think to answer this question, I think 5,000 cycles is what people have achieved as of now to the best commercial lithium-ion battery. So that is determined by, as I shown earlier, I think the lithium goes from shuttles between the anode and the cathode. It's not that every time 100% of the lithium will go to the anode and reverse. So it's only a fraction. I think at any given time about 90, let's say if you have let's say 100 lithium, about 90 lithium will go to the other side. And this process will continue over a period of time. So the 90 will become 80, 80 will become 70, and it will reduce. Okay, that's why if you buy a very new mobile phone and it has a lithium-ion battery, initially you need to charge once in 2-3 days. I think that charge will reach time. After 1 or 2 years, you see that you might have to charge every day. Your life will, the lithium-ion battery life will go down. So this is the shuttling over a period of time degrades, because some of the lithium will stick into that matrix which will not come out and which will not participate in the reversible process, and that's where your degradation will happen. What is the?
Voltage level
Yeah, voltage level will also go down. Slowly that will, voltage will not have much impact, but your current level will go down drastically. So over a period of time, I think, 5,000 cycles is a good protection, you can say, above which it will die.
While charging lithium-ion batteries, should we wait for complete discharge or we can charge in the middle, say 50-60% also, can we start charging?
So that is one advantage with lithium-ion battery. Unless a lead-acid battery, you have to discharge completely and charge it completely. That's considered as one cycle. If you do that infrequent charging, discharging, the battery will die very fast in a lead-acid battery. But lithium-ion battery, yes, that can be avoided. It will not die as like your lead-acid battery. Even partial charging is still fine. So there is no problem with that. Yeah.
Any other questions? Students? Yes.
Thank you both. Like, it was a really good lecture, like presentation what you gave, both of you. Thing is that the question I have is, you said like lithium is not really good to use right now for mobility of buses and everything. So how about like methane gas, like gobar gas, biogas, could it be used? And could buggies, like biofuel, can it be used for mobility? I would like him also like to.
Do you want to answer?
Yeah, I know like there is no such as such called single solution for a problem. So like for example, we have power production now. We have hydro, sun, wind, nuclear, everything. So do I think e-vehicles can also have that sort of option. So it's essentially replacing the LPG gas with methane. That's it, as simple as this. So we already have natural gas autos running all around Chennai, and we have gas filling stations. And the only thing is that we have to have a reliable supply of gobar gas, which can run the vehicles. I'm sure people have tried. It's not something like really complicated. It's just that already we have engines running on LPG.
Efficiency and cost efficiency.
Yeah, exactly. And energy security. Because natural gas, if you sign contract with any countries, I think we'll be constantly getting all those things, whatever the gas amount we are asking for. Whereas this one, we may have insecurity, like how much we can get. Like, can we get all the time the same amount of energy that we are asking for? So that may probably not these kind of technologies. Yeah, Raghu, you want to add something?
Just to add on, I think I've showed in my slides, I think earlier time lead acid battery was used for mobility. That picture, if you remember, there is only one person who can sit in that vehicle because the entire vehicle is full of batteries. You don't have people to sit in. The same thing will happen, though what I talk about energy density. So the energy density for the biogas or gobar gas, so that are much lower. So in terms of stationary application, it's okay because you don't have issue with the space. But when you talk about mobility, your car has a very fixed space. You wanted to utilize that space alone for your power needs. So that will have an issue in terms of running your car. So the battery vehicle currently facing, because if you entirely fill the car with the battery, then nobody can sit. So only within that limited space, you need to accommodate both your charging solutions and your battery management system and so on. So that is a limitation which somehow it will take a long time before any of the other technologies like particularly the gas technology other than the LPG or CNG will have to come. Even the hydrogen is a very good gas, but the compressing hydrogen requires a lot of effort, and storing in a very compact space again require a lot of effort. That's why I mentioned briefly about fuel cells, which is one of the core domain I work on. So that will take again to come into India another 100 years or so. It's in a commercial scale, it will take. So that has hydrogen stored in your vehicle. So instead of the conventional batteries what we have now. So that will take a little long time because there are issues to bring into a smaller compact size.
Any other questions? Yes, Ramanujam.
If we are thinking of large-scale battery use, what about waste disposal? I mean, we'll also have large-scale batteries. When they run out, what do we do? Or is there some plan for that in some way that you can explain?
So the one thing which Aravind mentioned, so India doesn't have any of the lithium resources, like we don't have places where we can extract lithium. Once we import all this battery, if you have a very good recycling system, because lithium ion battery has nickel, manganese, cobalt and lithium. So if we can use the waste battery as a ores or for processing, reprocessing this lithium, you can extract the value added metals from lithium. I think that's the best thing. But so you have to think about how we can recycle this. So there are people or research labs which are working on it, and there are also 1 or 2 companies in India who have invested in this technology. But we should think about recycling. As far as lead acid battery is concerned, I think we have 98% recycling is possible. But in lithium ion batteries, it is not that high. But still, I think we should be able to, I think if the technology develops, I think we should be able to get at least 80% recovery for the metal can be recovered from lithium ion batteries.
So,
Any other questions?
Just to add on something to that, I think nowadays what's happening is all the big electric vehicle manufacturers in India, whomsoever are planning to step in or stepped in, so they're trying to find out a second life for the batteries that's being used in the electric vehicles. So they're trying to use them in telecommunication like towers and all those places. After that, after 10 years after their operation, I think typically they sign contract with any country they're importing the battery from. They'll send it back to the company wherever they're importing it from, so that it's their headache. So that's the kind of policy that we have at the moment in India. And that's at least like big EV manufacturers are trying to impose this kind of policies, so that we will not end up with a lot of lithium junk out in here until we find our own technology.
What is the cost of these cars, Nissan or BMW, electric cars?
Okay. So, excluding the taxes, I think we'll put it that way, because I don't know, like import taxes might be like almost 100% for these cars. So that's around 40 lakhs roughly. I think we did like some 2 months ago, if I remember correctly. BMW i3 is around 40 something. That's more like Alto. Very, very small one, and which we are getting it for 4. And Mahindra Verito comes for like roughly around 12 to 18 lakhs.
Okay.
And Kona, is it Hyundai? Yeah, Hyundai, I guess. They are selling it for 36. It's more like Innova type vehicle. So no, sorry, it's not SUV. It's kind of hatchback, but slightly larger hatchback. Okay. So that comes for 36. And they have roughly around 20 to 30 kilowatt hour batteries inside. So, yeah.
There was this car, Reva, which was going around everywhere.
I have no information about it, sir. I was too young at the time to really even know that, so probably I should look into Google to find those information.
Okay, fine.
Yeah. Okay.
Tesla costs about 75 lakhs.
Oh my
So
God.
that's 100 kilowatt hour.
100 kilowatt.
It's on a higher side. But yeah, Nissan Leaf is much lower, about 30 lakhs you can buy a car.
They are essentially hatchback.
Yeah.
So 3 people
The
can.
Tesla is a high-end model. It's
Okay, high-end model. Okay.
a sedan model.
Okay.
Cybertruck is there. So obviously Cybertruck can carry all of us.
Okay. Okay. Questions? Any other? There is one. Okay.
Good evening, sir. My name is Kalaimani Karunanidhi, working as a marine engineer in British Petroleum, London, sir. Sir, apart from SICRI in Karaikudi, which one is the major laboratory in our country which plays a major role in the field of electrochemistry, sir?
I think several IITs, even NITs, they do electrochemistry in general. But they have SICRI has a SICRI battery unit in Tharamani. So they have 2 units. One is on a fuel cell division and another is the battery division. So they have a specialized, I think they have all the equipments which is just near Ascendas. So they have manufacturing capability also. Now I think earlier this year there was an large funding was given to them to manufacture batteries. Even VSSC, they have the facility. Though it's not for commercial deployment, they do it for their own need. But I think there are research labs, yes, there are labs which are involved in battery research.
Thank you, sir.
Sir, thanks for the eminent lecture, sir. Professor Chandran, I have one question. You showed one compound, some cesium, platinum, indium. I think you have to thank all your funding agencies. Indium, platinum, I think you can't think of it is much, much expensive, no, sir? You are converting H2O to hydrogen. Do you think it is really is it really worthwhile to even get hydrogen out of water using these unimaginable thinking compounds, sir?
Yes. So
what must be the rate you would have used, no, sir? Some 1 or 2 grams of it.
Yes. So I can comment on this. At the moment, I think we don't look into the prices. I think typically we more look into the design of materials so that we get a specific design. We don't care about what is
commercially, commercially you don't think that it is viable, no, sir?
At this point of time, no.
No, sir.
At this point of time, definitely no.
Sir, just
but
one more
LED,
question,
by
sir.
the way, the indium thing that you mentioned, we have the LED.
Indium is much more costly than gold, no, sir?
No, but that's fine. But we know the present day LEDs, the white light emitters, they have cerium doped yttrium, yttrium aluminum garnets. So those are all quite expensive also. So the present, in terms of white light emitters, presence of indium is not going to add much difference. Whereas in terms of the energy generation, energy sector, the fuel and other things, definitely I think this is still very nascent stage. We have a long way to go.
Only one more question, sir.
Yes.
Professor, sir, you focused on lithium, and the second lecture was on zinc. There are many metals in between lithium and zinc, beryllium, boron, you have scandium, titanium, many are there. Can you please throw some light on these metals? Are they not useful, even a bit of it, sir? One end at lithium, one end at zinc. In between there are many metals. Have you done some research, or is there any material on these things, sir? Thank you.
Yeah, again, it's depending on the application. There are materials like silver is also being used. I think earlier even Volta used silver. There are silver is used. Nickel is widely used. So there, manganese. There are several metals are there, but people look at both in terms of weight and also in terms of the ability to electrons. So in that, when you have a combinations, I think it boils down to only few metals. And that's why the people is always have a choice of selecting few metals than going with every metal. But even lithium-ion battery, it's not just lithium; it has several metals. So we have manganese, cobalt, nickel on different composition, and people also wanted to add few more metals to it. That's an endless possibility. Actually, in a lithium-ion battery, the amount of lithium is only 3%. The rest and all is other metal. So it's only the lithium which shuttles between the two anode and the cathode. The total content of lithium is only about 3 to 5% to the maximum.
Okay, you can ask.
So you know that the airline industry is the biggest polluter. Is there any way that we can use electric batteries in airplanes and make Greta happy?
Airplanes, Boeing, there was one version, Dreamliner, which came. So that is down now. That was tested with lithium-ion batteries. The first aeroplane.
On a commercial scale, is it feasible for?
No, they tested it, but there were problems. A couple of occasions, I think they had fire, so they grounded that. I think nowadays the liner is no more there. So there were something. Maybe the one other problem we have is we try to take to a commercial scale much earlier, like before a complete research is done. So some people wanted to take to a commercial scale. And that is where this, before we understand the process fully, it goes. I think some more time is required before these go into the air thing.
Thank you.
But again, these are only to, as of now, they power the auxiliary power. We cannot have an engine running with battery. I think,
So maybe you have seen Solar Impulse plane that the Swiss guys ran. I think they crossed Atlantic Pacific. They took a whole turn. What they said is they just only one person can fly, and if it just gets dumped into the sea, I think they have a parachute to escape. But the amount of power required to give the thrust to the engine is extremely high. Batteries cannot run at the moment. To make her happy, we have to see the technology. It's about are you ready to kill yourself in flying an EV-based powered aircraft? Emitting a bit of carbon dioxide and keep yourself safe. So it's just about balance between the two.
Well, at the other end, drones are being used with lithium-ion batteries.
Yeah.
Drones do. We can think of usages for the lithium-ion batteries up to correct levels.
Yeah.
Is there anything else? Yes.
No, I'm like curious about the bio part of the collaboration you are doing with the medal. Can you like a little bit discuss on that? What you are working on, or you are like partially not even started to work in this lab?
No, we do have great facilities and then started working on it. I've shown some results also. Like we tried to the current generated by respiration and photosynthesis going on. Can we learn? It's not thing. There are something that people outside IIT Madras think make it commercially available. But if you try 1,000 stuff, things that can go out, and we also try to understand fundamentals. So the entire goal of this whole project is to understand how nature does this year after year, decades, like years after, several centuries after centuries, without like reducing their efficiency. They just reproduce with the existing things that are in the atmosphere. All is to understand how charge can be transferred out of the cell. That's the only thing to study here. Yeah. So I'm shining light onto microbes. So specifically working on cyanobacteria synecocystis, where we shine. So we have a mission called, we just going to order that, scanning electrochemical microscope. So what we do is we shine light onto the microbe part, and then we freeze our flagella is conducting there. So and try to see when you shine light if flagella is trying to get the electrons to the outer part of the cell. So only cyanobacteria has that advantage. Let's take the chloral. So the goal is more like have water everywhere and algae everywhere. You put 2 electrodes and get. It's a kind of fiction thing that we have in mind at the moment. Years, if we could realize that, it will be nice. But as of now, very fundamentals. Yeah.
Yeah. Hi, sir. Now that e-autos are running around in Chennai city, even they need to be recharged. So my question is about the charging stations. How are the charging stations powered? How do they get power? By burning coal? Or?
Yes. So now it's fossil fuels only. So we don't have an alternative, at least for Tamil Nadu. But Tamil Nadu also has a lot of wind power. I think it is one of the leading states in India for a wind power. But I think by that it doesn't reach Chennai. By the time I think the wind power doesn't reach Chennai. The EVs, I think, swapping mechanism. So I think it's been practiced in IIT. So you don't need to. Charging is done. So you swap the batteries. You go to a petrol station like that, they have a charging station. There is already a charged battery is available. It takes about 3 to 5 minutes to swap the. It will run like a regular auto rickshaw.
Okay, thank you very much. Now we are reaching the end of the program. Mr. Vijayan will probably make some comments and also vote of thanks.
I have a couple of announcements. I would say that it's not announcement, it's a request. Nice. Please fill up your feedback form. That will help us to organize it better for the subsequent events. My second request is please become a member of Tamil Nadu Science Forum. We have the forms available in our desk. Please fill it up. Some of you might not have registered, or some of you might not have filled up the registration forms. If you leave your address and email ID and phone number, that will help us to communicate you for our future events. Please do it. So the registration facility is available, still open in our the desk outside. Please do that. Yeah. So vote of thanks. First, I would like to thank Dr. Raghuram and Dr. Aravind. They have immediately accepted our request.